This is a feedback model answer for question 3 of our core component Mark 1. So core component Mark 1, question 3. And we've got a very typical diagram here, enzyme and an inhibitor. And so as soon as we see that, we're thinking, right, inhibitors, competitive, non-competitive, what's it going to be? And you're already, even before you look at these questions, you're going, right, molecule X, could that fit in there? Or would it fit somewhere else? That's what we're thinking. We're thinking about words that we're going to use in an enzyme question. We might use active site. We might use words like binding, enzyme substrate complex, substrate product. Words like that should be popping into your head as soon as you see this question and that diagram. The type of inhibition, well, this molecule here would fit in something something like that. So that's that molecule there. Not a great diagram. So that would fit in there. So that would be competitive, because then the substrate is possibly, might be that sort of shape, and that would normally fit in there, but it can't because the inhibitor's there. So type of inhibition, that is competitive. How molecule X would inhibit it. We've got 2 marks available here, so we need to say that stage there and this stage here. So we need to say that the inhibitor fits into the active site. Be careful with the word bind, because that sort of indicates that there's something more than that going on. So just fits into the active site is best, and then it prevents our substrate from binding with the active site. So prevents substrate from binding with the active site, or we could say it blocks the active site, or words to that effect. Then we've got a part B, some sort of graph, and hopefully your graphing skills, you've done all the maths homeworks and you're good at those. And what's this question? It's about temperature, and very slowly below 5, has an optimum rate of working at 40, completely denatured at 50. Draw a grid to show the curve. Right, okay. So I think they're more concerned about the shape of this curve rather than super exact plotting. In fact, we haven't really got any numbers for the y. So what have we got on the x? We've got temperature, and that's in degrees C. And how many squares we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to fit 50 on there, are we? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Keep looking out, you play tricks with your eyes, these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's the last one. Okay, so we've got 0, 10, 20, 30, 40 and 50 there. And what have we got? Rate of activity of the enzyme. So up here we've got rate of activity of the enzyme. And what information have we got? Very slowly below 5. So you draw this in pencil actually, so you can rub it out if you're not happy with it. So below 5, so there's 5 there. So below 5, very, very slow. Okay, well we'll have that as very slow. Optimum is 40. So we don't have any numbers here, so I'm going to have maybe something up there. Optimum 40. And this shape here will be kind of going up slowly and then reaching its peak at 40. So that will be sort of a compact, concave shape going up. This is very sort of that shape there. And then what other information have we got? Completely denatured at 50. So above 50, this rate has got to be 0. So this would sort of go down rapidly to 50. So a shape sort of like that. We could have a kind of a wider kind of optimum there. But what are they actually looking at? They're looking for this curve starting to rise above 5. We're looking for the optimum at 40, and then it's got to go down to 0 by 50. The shape of this going up here is not a straight line, so that's concave, and labelling for the axes. So there's 1, 2, 3, 4, 5 things there, and you just need to hit 4 of them. And I think I might have just about hit 4 with my amazing diagram there. Why the enzyme works why the enzyme works very slowly below 5. This is just classic enzyme stuff, and so if you've done enough questions you'll be absolutely fine with this. So low kinetic energy, and they'll probably give it you for that, but then your explanation is molecules moving slowly, less chance of a collision, collisions have lower energy, that sort of thing. So molecules move slowly, less chance of a collision. Those sort of answer. Collisions don't have a lot of energy and so on. What happens to the structure of the enzyme when it is completely denatured? Well, from your theory, you know that hydrogen bonds are breaking, which is going to change the shape of the active site, and then that changes the tertiary structure. So and then you got the effect on the enzyme. But it just says what happens to the structure, so we don't need to talk much further than that. So things like hydrogen bonds break, and the shape of the active site changes. The tertiary shape. I'll write that. The tertiary shape changes. So an absolute classic enzyme question there, which you should have scored reasonably highly in.